Some of the hidden energy costs of big industries are, here are some examples like cars. They take about 30,000 kilowatts to build one. Takes about 1,000 kilograms of carbon dioxide per passenger for an airplane. That's how much energy is used. And batteries are used, uh, batteries are mined, which usually takes up a lot of energy as well. So companies manage to hide these costs through carbon outsourcing by moving their factories to other places in order to avoid reporting from like people nearby. They also use something called greenwashing, which is creating claims that their that their product is eco like friendly to the environment without any proof. And it also has misleading labels like natural or green without having any certifications or anything proving that. So, how does technology relate to this? So, technology uses data centers, and these data centers are huge, vast, usually requiring lots of power. Along with this, new technology like AI models take millions of liters of water just to train one. And tech just in general like uses a lot of energy. So the electricity being made requires these different hidden energy costs to be used. So here are some energy sources that power products. One is electricity, like powering the factories. Two is heat, which can melt or process items. Three is fuel, which usually helps with transportation. And four is mechanical, like producing products, packaging products, things like that. So here are some common products and hidden costs. So a t-shirt takes 650 gallons of water to make. A cheeseburger uses 660 gallons, and jeans take 1,800 gallons per pair. So now that we're talking about water, let's talk a bit more about the virtual water footprint. So the virtual water footprint is usually has these three formulas. So it's the total volume of fresh water used directly and indirectly to produce a product or service. So like how much water is used to produce something. And this includes green water, which is rainwater absorbed by the soil, blue water, which is surface or groundwater used in irrigation, and gray water, which is the volume needed to dilute pollutants. So we use formulas like the crop-based model, which uses evapotranspiration, which is the amount of water a crop needs for growth and development through evaporation, and yield, which is the amount of crop harvested per unit. So another critical component of the water footprint formula is the gray water equation, which is where we calculate how much clean water is needed to reduce pollution to safe levels. So why should engineers care? Why should people working in electrical engineering or you working with energy care about this? The reason is because even a simple t-shirt can cost nearly 3,000 liters of water to produce, and this water is embedded invisibly throughout the supply chain. So all products use it. Everything that goes around uses water and creates a virtual water footprint. So this hidden cost matters when designing sustainable systems or evaluating energy technologies to make sure that we can sustain the amount of water we have while reaching maximum efficiency. So the hidden water energy cost of circuits. So on this slide, we're looking at something that's often invisible in the electrical engineering conversations, the water footprint of the technologies we designed. We talked about circuits in our last meeting. So this is going a little more into depth of how it relates to these hidden energy costs. So on the left, you see a 300 millimeter silicon wafer. These are used to create chips in everything from smartphones to electrical vehicles. What's surprising is that the manufacturing of just one of these wafers can require up to 16,000 liters of ultra-pure water. However, the water itself is not the full story. If you look to the right, the diagram shows the ultra-pure water treatment process. And there are many steps, and each of these steps use electricity, not just to push the water through the filters, but to run pumps, cooling systems, and chemical control systems. The total energy consumption for producing ultra pure water can range from 9 to over 90 kilowatts per cubic meter, depending on whether it's cold or hot ultra pure water. That means that using a single chip wafer might carry an embedded energy cost of hundreds of kilowatt hours just from the water purification stages itself. So we've learned all of this, but what should we take away from this? First, we often focus on a circuit's power consumption during operation, milliwatts, joules, battery life, but long before that chip is powered up, it's already raced up a large environmental energy cost through its fabrication, and water is a big part of that. Second, this embedded water energy cost doesn't show up in a circuit diagram or spec sheet. It's hidden, but it's real. So we have to remember that. The more we manufacture, the more energy we're quietly spending. Third and last, as electrical engineers, people need to expand their design perspective. Optimizing for power efficiency isn't enough. We also need to optimize water efficiency. So this is where sustainability and electrical engineering intersect, not just in the circuits we build, but in the materials, water, and energy that make them possible.
All right, so we just discussed how electricity and sustainability are directly correlated. But now let's talk about the different circuits that we use and how they may affect our um how they may affect our uh society. So, what is a parallel circuit? Uh just to make sure, can everybody hear me?
Yes.
Okay, good. All right. So let's keep going, right? What is a parallel circuit? So, in a parallel circuit, components are connected across common points, forming branches, right? And each branch provides its own path for the current to travel. So this means that if, let's say, one component fails, the others still receive current, which is why parallel circuits are used in homes, cars, and electronics. So let's look at the picture on our screen, right? In a parallel circuit, our bulbs are called resistors. And we see that in a circuit, electricity flows from the negative terminal side of the battery to the positive. And so as the electrons are flowing through, they stop at both the D and H and flow through the batteries. And we see that, let's say if our first light bulb is not working properly, it'll continue on to the second light bulb. And that first light bulb will not affect the second light bulb. So one light bulb does not affect the other, and the circuit still works. All right. So let's go to the next slide and let's look at a reminder of how electricity works. So, electricity is like a water hose. Electricity is the movement of electrons through a conductor, like a wire. The voltage is the pressure which pushes the electrons. Higher voltage means more energy. And now, current is the rate at which these electrons flow through the wire, and it's measured in amperes. Our resistance slows down the flow of electrons, which is measured in ohms. So electricity is like a water hose because if you increase the pressure, voltage, more water, current flows. And if the hose is narrow, there's a higher resistance, which means less water flows. So if you look at our picture, let's say the hose is filled with sand. A lot of water is not going to be able to get out. And the same thing is with electricity. If there's more resistance, less electricity can flow through a wire. And this is an important thing to consider. So, in our next slide, we're talking about how does electricity flow in a parallel circuit. So, let's visualize what's happening inside a parallel circuit when the battery turns on. The electrons have a negative terminal side of the battery, and they flow towards the junction, the point where the circuit branches out. So in this step, the current splits up. And we see that from our 9-volt battery in this picture on the left-hand side, the electrons flow through the wire and they go towards the 7, 6, and 5 junctions. And at each of these junctions, the electricity splits up. Each branch provides a separate, independent path for the electrons to travel. If you've got, let's say, 3 branches, the current divides across all 3, just like in this image. The amount of current in each branch depends on the resistance in that path. So in each of our paths, we see that there's a 10 ohms resistance, a 2 ohms resistance, and a 1 ohms resistance, right? So think about it like the water hose. If we have a lot of sand in our water hose, less water is going to flow through. And the same thing in this parallel circuit. In our first path from 7 to 2, we have a 10 kilo ohms resistance, meaning not a lot of electricity will flow through, right? And then the 2 and 1 kilo ohms resistance, a lot of electricity can flow through. So, on this next slide, we'll talk about currents in parallel circuits. Current is divided across the branches. More current flows where there's less resistance, right? As the battery pushes the current into the parallel network, it chooses different branches to flow through. The current drawn from the battery is the sum of all of the branch currents. Again, think of it like the water pipes. If there's a lot of pipes, there's more paths, meaning that more water can flow through overall. So let's look at the next slide. And this slide talks about voltage being constant across branches. So this is where parallel currents really shine, okay? Each branch is directly connected across the battery terminals. So they each receive the full voltage of the source. This means if each device or resistor can operate at full power, it's true, regardless of the others. So if one bulb burns out, the rest stay on because they have their own independent path. So in this image, we see that the resistors R2, R3, and R4 each have their independent path, and that means that if R2, let's say, burns out, right? R3 and R4, electricity will still flow through because they're connected in a bigger loop with R1, which is our battery. And in this scenario, Ohm's law, which we covered in our last lesson and our in-person meeting, still applies. So now we can talk about series circuits, all right? So series circuits are a single path for current to flow through, right? And one second. Okay, yeah. Okay, so series circuits are a single path that are connected to an end-to-end single loop. And the battery provides the initial energy, and the current flows through each component in a sequence. So in our last in-person activity, we built those circuits by hand, and it had a battery and then one single light bulb, right? That was a very, very simple circuit, and it was a full circle. In this simple series circuit, it's a series of different light bulbs, right? We have lamp A, lamp B, and lamp C. The battery provides electricity through each of the light bulbs. And so let's say in our scenario, lamp A stops working, right? Electricity can no longer flow through it. Well, guess what? Even though lamp B and lamp C can still work, they won't work because electricity can never get to them. So the key point in a series circuit is that there's only one path for the current. So if one component fails, the whole circuit stops working. So we can look at, in the next slide, currents in a series circuit, right? So in a series circuit, the current is same throughout the entire circuit, right? All components experience the same circuit, same current, because there is only one path for the electrons to flow through. And in this image, we have a direct comparison between a series circuit and a parallel circuit. At the top, we have our series circuit, which shows the only path of electricity, whereas on the bottom, the parallel circuit, it shows us multiple different paths. So each light bulb, R2, R3, and R4, is demonstrated how it would look like in the respective circuits, right? We know that if R3 stops working, R4 won't work, nor will R2, because the whole circuit will stop working, right? It's, if you remember in our in-person activity, if we stop connecting the light bulb, the circuit won't work, right? And it's the same thing here. The circuit, all the electrons cannot flow through the circuit. That's when your circuit stops working. And that's not the case in our parallel circuit, right? So in our next slide, let's look at divided voltage across components. As the current flows through each component, it loses energy in the form of a voltage drop, right? The voltage drop across all components equals the voltage provided by the battery. For example, if you have a 12-volt battery, the voltage drops across all components must add up to 12 voltages. Higher resistant components will cause a larger voltage drop, right? So voltage is the amount of energy each charge carries, right? So in a series circuit, the total energy from the battery is shared across all components because the resistor with more resistance slows down the current more, it uses more energy per charge, causing a larger voltage drop. So think about it like this, okay? If I have a large, heavy box and I need to push it across this surface, let's say we have surface A, which is a stone surface, right? It's the road outside. It's going to take me a lot of energy to push my heavy box across the surface. And it's the same in a circuit. If I have a higher resistance, it's going to take me a lot more energy for my electricity to flow through. But let's look at it like this. Let's say I have surface B, which is a slippery, smooth, polished surface. It's going to take me less energy to push this heavy box across the surface, right? And so in a circuit, if I have a low voltage and a high voltage and a low resistance, it's not going to take me that much energy to push my electrons through the circuit, right? So let's do a recap of our key concepts. In our next slide, we're talking about how our series current works, right? A quick summary. In a series circuit, the current is identical throughout all components. The voltage is divided across each component, with larger resistances causing larger voltage drops. This was our heavy box analogy in our last slide. Total resistance is the sum of all individual resistances in the series. And if one component fails in our simple series circuit, the whole circuit is interrupted because electricity can't flow through. Simple series circuits are very easy to build, but they're not as reliable as parallel circuits because if one thing fails, the whole thing fails. But in a parallel circuit, that's not the case. So in our next slide, we have a direct comparison between our series and parallel circuits in a simple diagram. So you can see here that the difference between how the series and parallel circuits looks. In just an image, we see how complex it is, right? the parallel circuit looks much more complex compared to the series circuit. And these are our different equations for calculating the voltage, current, and resistance. You don't need to focus on it that much. We'll focus on it much more in our in-person meeting where you go hands-on with the circuit. But let's just consider the important feature. If one component burns in a series circuit, the whole circuit becomes inactive. But if one component in a parallel circuit burns, the current continues to flow. Nothing bad happens. So remember this and consider this for our next activity. This is very important and it's a key concept in electrical engineering and circuits. So we discussed our different circuits, but it's also important to consider the cost. As we learned at the beginning of the slideshow and as Akshit taught us, it was very hard to, really gauge how much energy we're really using when we use circuits. So in our next slide, we'll consider the costs. So cost-wise, series circuits are cheaper because they require less wire and are simpler to design. It makes them useful in small or low priority systems. Parallel circuits cost more upfront due to extra wiring and design complexity. So if you think about it, when we build something on hand, a simple series circuit would cost maybe, let's say, $3, right? Considering all the wires, the batteries, and the light bulbs. Now think about it if electrical engineers go to build a simple series circuit in a house or in a skyscraper. It'll cost 100 times or 1,000 times more expensive. And we have to look at it like this, right? The way we produce our materials comes from a factory, and this factory may use, you know, fossil fuels to produce these resources. And using this, we're hurting the environment. We're using a lot of water, right? We saw that a simple t-shirt costs so many gallons to make so many gallons of water. Imagine a circuit in a skyscraper, right? So when you look at an electrical engineer, they have to consider a lot of things when they're building a circuit for a building, right? You have to look at, okay, do I need a simple circuit or do I need a parallel circuit, right? Which is going to be more expensive, which is going to be more efficient, and how am I going to power these circuits? What is the best way to reduce my environmental footprint when I'm building these circuits, okay? So that's that for the costs. Akshit will now cover our next in-person activity in which you guys will be considering efficiency and costs.
So for our next activity, we will be using snap circuits to visualize reducing hidden energy costs by using these circuits. So these circuits work similar to what we were talking about earlier, parallel and series circuits. And this is a perfect way to introduce making more reliable and more efficient uh, circuit ways in order to reduce hidden energy costs that we see while keeping the same function. So what kids will be doing is they'll be using these blue connectors, which will serve as the circuits to try and make different function try and make different functions work. But the problem is that each of these circuits will have a certain energy cost, maybe in water, maybe an amount of CO2 made, something like that. So we have to make sure that we reduce those costs as much as possible and make our environment safer and more clean. So that will be our next activity for our meeting on April the 30th. That's all we have. Thank you.